Okay, so welcome back to our second online lecture. It's going to be on lesson 17, stoichiometry. I've already got the assignment up there and available for you, so you can start immediately following this. Remember to keep up with your assignments as we go. And yeah, this one's going to be about lesson 17, and I'll try to get as far as I can through it. I don't think I'm going to completely finish it, but we'll get pretty close. So what we're going to be doing today is we're going to be talking about stoichiometry, which is a really central topic to chemistry. So we've already been talking in lesson 16 about molar masses and how to use them to get between the grams of something and the moles of something. And the reasons why we want to do that is because we want to figure out how many atoms or molecules of a compound that we have to work with and that can make other molecules. Remember previously we worked on balancing chemical equations, and those told us how many of one molecule could be used to make how many of another. But this is extremely important to our everyday lives. For example, the microphone I'm talking into right now has a casing that's plastic that was made out of hydrocarbons, as you guys learned about before, that were dug out of the ground. And they were made into plastic. So a really important question in a lot of production as well, how much of this hydrocarbon fossil fuels essentially do I need to make a certain amount of plastic? Cool, all right. For pharmaceutical drugs, I know many of you are interested in the healthcare profession. For medications, these often involve a series of chemical reactions, and you need a certain amount of a starting material in order to make the medicine that you're trying to make. And it's important to figure out how much of it you would need or how much medication you could make out of this starting material. All of the consumer products we buy, almost all of them, have a kind of stoichiometry calculation behind them to figure out how much stuff you'd need to make some other stuff using chemical reactions. Okay, so just to go back real quick to how to read a chemical reaction. So last time when we were balancing chemical reactions, we mainly talked about reactions in terms of individual atoms and molecules. So one way to read a chemical reaction like the one we had here was that we could say, well, we have 4 atoms of lithium here. So that's what the 4 means in the balanced equation. And here's the Lewis structure of those lithium atoms right here. And those are reacting with 1 molecule of O2, and the Lewis structure for that is here. And in the end, they're producing 2 formula units, as we're going to call them, of ionic compounds. Remember, for covalent compounds, they come generally in molecules, but ionic compounds don't have molecules, so we call each unit of the ionic compound a formula unit. We've got 2 of those, as we can see here, and each one contains 2 lithium atoms and 1 oxygen atom in it. And we've got 2 of them, 1 here and 1 here. Now, having the chemical reaction does describe what's going on in terms of individual atoms and molecules, like we see here, but realistically, we're never going to be doing chemical reactions with individual atoms or molecules. They wouldn't make enough stuff for us to really care. But when we balance the equation like we had before, we balance it to make sure that the number of atoms that we start with is the number of atoms that we end with, and that they're all the same and the same number, because chemical reactions don't involve making new atoms or destroying atoms. It's just atoms being bonded in a different way. So one way of reading this reaction was to say that 4 lithium atoms react with 1 oxygen molecule to produce 2 formula units of the lithium oxide compound, ionic compound. But the more useful way a lot of the times for reading this is scaling it up to a mole. So just like we could say 4 lithium atoms reacts with 1 oxygen molecule to produce 1 lithium oxide, we can scale everything up by a mole and say 4 moles of lithium would react with 1 mole of oxygen. and produce 2 moles of lithium oxide. And so that's saying this in terms of moles. And that's going to be a lot more useful to us because, as you saw from experiment 3, a mole is like a handful of stuff, which is a useful amount of stuff to talk about, much more useful than individual atoms and molecules. So remember that in the balanced equation, the coefficients tell us how many of each of these atoms, how many moles is more useful, of each atom or compound that will react or be formed relative to each other. A chemical reaction really is like a recipe. It's basically the same thing as a recipe. It's just written in terms of fancy chemistry terms. So to describe what's happening in a reaction and do stoichiometry, it's useful to use like a kitchen cooking type of analogy here. So the chemical reaction, or the chemical equation rather, for making pancakes would be you take 1 cup of flour and 2 eggs and a half a teaspoon of baking powder. These are your reactants in the equation, in the reaction, to make 5 pancakes, which are your products in the reaction. So the chemical reactions, chemical equations are just the same way. You've got some reactants, which are your ingredients essentially, and you've got some products here that are made. So let's say we have plenty of flour and we have plenty of baking powder. We got tons of it. We got a whole big bag of flour. We got plenty of baking powder, but we've only got so many eggs, which is often the case in the kitchen, right? And it's often the case in chemical reactions too, is that one particular reactant is much more limited than the rest. So we would focus on that one ingredient and see how many of our product can this one ingredient or reactant make. So just looking back at this balanced recipe here, it takes 2 eggs to make 5 pancakes, assuming we have plenty of the other ingredients. So 2 eggs makes 5 pancakes. That's going to be our relationship that we're going to use. It's going to be a conversion factor. So the recipe shows the numerical relationships between the pancakes ingredients. Same way chemical equations show a relationship between all of their ingredients, their reactants and products. If we have 2 eggs and enough of everything else, we can make 5 pancakes. So this is our conversion factor. Basically 2 eggs equals 5 pancakes. So we need 2 eggs per 5 pancakes that we make. That's a conversion factor. 2 eggs per 5 pancakes. Now let's say we're starting with 8 eggs and we're asked to determine how many pancakes could we make. Well, your relationship that you had on the last slide was 2 eggs per 5 pancakes. So that's the relationship we're going to use as a conversion factor. Our data here will be 8 eggs. 8 eggs is our data. So we write the 8 eggs here first. We always write the data first, number, unit. But then we're going to apply our conversion factor. And when we do, we want to make sure, like always, that the units cancel. So what is the unit that's going to go down here?
Eggs.
Eggs, yeah, because we got to cancel, right? Every day we're canceling. We got to cancel eggs.
You know what we should buy?
So the
apple cider vinegar pills.
We're going to put the number that went with the eggs in our ratio next to it. So that number was 2. And then we know that 2 eggs in our recipe means, canceling the eggs here, that we can make 5 pancakes. It's 5 pancakes per 2 eggs. And so the eggs cancel and we get pancakes. Then we're going to multiply and divide. Remember, you don't have to do anything fancy. Just take anything that's on top and press times before you enter it in the calculator. And everything that's on the bottom, press divide before you enter it. So 8 times 5 is 40. Divide by 2 is 20. And our unit we have in the end is pancakes. So our result is 20 pancakes. Any questions on the pancake problem? Okay. So let's now apply this same process. It's going to be basically exactly the same, but we're now going to apply it to a chemical recipe, a chemical equation. So here's a similar type. Our last question was how many eggs or how many pancakes could be made from 20 eggs? This question asks us how many grams of lithium would be needed to react with 45.3 grams of oxygen, given that reaction we had at the beginning. Now, the first step that we're always going to do here is if we're given grams like we're doing here, that is not so helpful to us because the chemical equation is going to tell us how many of one molecule or atom is needed and how many can be made. So what we need to do is convert from grams to a measurement of how many. And a chemist's favorite measurement of how many is the mole. So we're going to convert between grams and moles. How do we interconvert between grams and moles? What quantity do we need to go between grams and moles?
Molar mass?
The molar mass, yeah. So that's what we're going to be using. We're going to need the molar mass for step 1, definitely. Good. Okay, so we're going to use the molar mass of the compound to go from grams of that substance to moles. So we started with 45.3 grams of O2, oxygen. And we want to go from grams of O2 to moles of O2. So we're going to apply the conversion factor here. And the unit that's going to go on the bottom, we already know it. We don't even have to turn on our brain. We know that whatever unit is here, it must go down here so we can cancel. So our unit will be grams of O2. But we need to know what number goes with that. And for that, we're going to have to calculate the molar mass of O2. So if we have one O2 molecule, it contains 2 moles of oxygen atoms. And so we did a similar thing like this with iodine in the experiment today. So a mole of oxygen atoms weighs 16 grams, but a mole of oxygen molecules contains 2 moles of oxygen atoms. So altogether, a mole of O2 weighs 32 grams. So the number we're going to put right here is going to be 32 grams. And then that is equal to 1 mole of O2. Oh yeah, so grams cancel. Gotta make sure to cancel the grams. And that is 1 mole of O2. Okay. So now we should whip out our calculator here so we can do our division. So we're gonna have 45.3 divide by 32. And we get 1.415, and it goes on and on. Are we going to write all of these numbers for our answer?
No.
No, we've got to consider sig figs. So since we're multiplying, all we got to do is count the sig figs. The 45.3 has 3 sig figs. So we want our result to also have 3 sig figs. So we're going to do up to the 1. And since there's a 5 next to the 1, we'll round this up. It will be 1.42.
Oh.
And so let's write that down now. 1.42 moles of O2. How did you get 32? Good question. So the way I got 32 is if I have 1 mole of O2, that contains 2 moles of oxygen atoms. Now the 16 here comes from the periodic table. So each mole of oxygen atoms weighs about 16 grams. And a mole of O2 has 2 moles of those in there. We have 2 moles of oxygen in a mole of O2, 16 grams per mole of oxygen, rounded to 4 sig figs here. And we get 32 grams. Oh, okay. Yeah, I should have pointed to the periodic table there. Sorry about that. But yeah, so that's how we got that. Good, you're following along. Yes, I highly encourage you guys to follow along. Punch your calculator with me, Make sure you get the same answer. And ultimately, you got 1.42 out of our calculator, and the units were moles of O2. Any other question on this first step here? Okay. So that was step 1. Now step 2. And of course, oh yeah, just a reminder here, the moles went on top because we needed the grams to go on the bottom so that things would cancel here. So now we have the moles of O2. So what we want to do is relate that to how much lithium would react in this reaction. So we're going to use the balanced equation, because the balanced equation tells us the relationship between how many O2 molecules react and how many lithium atoms will react as well. So step 2 is always going to be relating moles of one thing to moles of another in the reaction. And so we will go ahead. Oh yeah, I don't know. Is it, when I say unmute all, is it forcing an unmute? I'm just trying to, yeah, control any noise levels here. Sorry, I don't mean to purposely unmute you. I was just trying to control, I didn't want to mute as few people as possible. Yeah, anyway. So for step 2, you don't have to unmute. You don't ever have to unmute. Yeah. If just there's too much background noise, I might mute it. Okay. So next, what we want to do is, get to how much lithium. So in the last part of the question, we got to how many moles of O2. But what we want to do is convert that to how many moles of lithium that would react, because the question asked us about lithium. So again, first thing we don't have to turn our brains on. We just know that moles of O2 here must be down here in order to cancel with moles of O2 here. And on step 2, we're going to be using the balanced equation. So this is the only time where we're going to look at the coefficients in the balanced equation here. And so since this is a 1 for O2, we're going to put a 1 next to the O2 right here. And also sometimes 1 is not written. So if 1 wasn't written there, of course it would be a 1. Next, the moles of O2 cancel. And on the other side, we're going to put however much lithium that would be reacting. And that lithium would be 4 moles. So we put the 4 moles of lithium on top. And now we're ready to multiply again. So let's do that. 1.42 times 4. That gives us 5.68 for our moles of lithium. And so now we can write that down, 5.68, and the moles of lithium is the unit. So now we have the moles of lithium. Yeah, you guys never have to unmute if you don't want to, by the way. I'm just trying to have as many people who want to be unmuted. But I do have to mute anything that's like a lot of background noise. Okay. All right, questions there? So now, by the way,
Okay. Oh,
oh yeah, question?
yeah. This is Ricky. So just we take the whatever the units are and put them pass them over.
Yeah,
This is what they're
that's the kind of cardinal rule of any conversions,
doing.
is that when we're doing them, just to go back here, before you even start, you already know what's going to go here. This will guide
Yeah.
you so you kind of can know what the next step will be, so that you can just write right away, boom, moles of O2. You don't even have to really think about that part. What you really have to think about is, well, what
Yeah.
is the proper number to go next to moles of O2? And what will be on the other side of the equation that will be equal to that in some way? So for step 2, because we're trying to go from moles of O2 to moles of lithium, our numbers will come from the balanced equation. So 1 for the moles of O2
Okay.
and 4 for the moles of lithium on the other side. Did that help?
Okay. Yes. Thank you.
Sure. Other questions? So that was the second step. But we have one more step, because we have moles of lithium now, but the question didn't ask us for moles of lithium. It asked us how many grams of lithium. So we need to go from moles to grams. Remember, whenever we're going between moles and grams, what we need is the molar mass. And where do we go to help us to calculate the molar mass?
Periodic table.
Periodic table, yeah. So we're going to be going to the periodic table. Fortunately, this time we just have an element. It's just lithium. So we can read the molar mass directly off the periodic table since it's just an element. So that's what we're going to do. So we'll look for lithium here, and there it is, lithium. And the mass is 6.94. Okay, 6.94 there. All right. And so that's what we're going to use. So we're going to apply a conversion factor even before we deal with the 6.94. We know that the unit here has to be the unit right there so that it will cancel. And we'll be using the molar mass, so we'll have the mass of 1 mole of lithium. Moles of lithium will cancel. And we saw from the periodic table just now, a mole of lithium is 6.94 grams of lithium. So the other side here will be the other side of the equals, 6.94 grams of lithium. And now finally, we have to calculate. So let's do that. All right, so 5.68 times 6.94. And we get 39.42. Or actually, we want to go to 3 sig figs, so it would be 39.4. Since this is a 1, we'll leave it alone. So right here, we're going to write 39.4, and our unit will be grams of lithium. 39.4 grams of lithium. And that is what the question asked for. So after three steps, we're finally where we want to be. So just, and of course, again, yeah, we made sure the moles were on the bottom so they'd cancel, and thus the grams were on the top. So we did this one step by one step by one step. In stoichiometry, there's always going to be 3 steps that are possible. And stoichiometry is kind of repetitive. It's always the same 3 steps. But the first step in this problem was we were given grams of O2 and we needed to go to moles of O2. So to go between grams and moles, we used the molar mass of O2. Then in the problem, we were asked about lithium. So the next step was to go from moles of O2 and relate that to moles of lithium. For that, we used the coefficients in the balanced equation. That is step 2. Use the balanced equation. 4 moles of lithium react per 1 mole of O2. Finally, we have moles of lithium, but the question asks us how many grams of lithium is that? So we need to go from moles of lithium to grams of lithium. Every time you want to go between moles and grams, you use the molar mass. That's the molar mass right there. And so you can do this step by step by step like we did, or you can do it all in one shot. It's really up to you how you feel like doing it. So I'm going to show you also how you could do it all in one shot. So here we have 45.3 grams of O2. That's what we started with right here. And we're going to apply a conversion factor for step 1. We're going from grams of O2 to moles of O2. We make sure the unit's the same. Boom. And then it's 1 mole, 32 is the number that goes with the grams of O2. We write that there. The grams of O2 cancel. And the other side of the fraction is the 1 mole of O2. Boom, right there. So we put it right there. That's the end of step 1. And we stop there and we calculate it, but you don't have to. You can keep on going if you want. You don't have to stop at any of these steps if you don't want to. Just know that for your next conversion factor, whatever unit is here, you must have the same unit right there. So it's got to be moles O2 down there. Now for step 2, we want to relate moles of the O2 to moles of the lithium. So to do that, to relate moles to moles, in step 2, it's always about using the balanced equation. So the number that goes next to oxygen will be 1. 1. And then the other side will be the moles of lithium. So it's 4 moles of lithium per 1 mole of O2. So the other side is the 4 moles of lithium. And so now we're at moles of lithium, but that's not what we're asked for. We're asked for grams of lithium, so we don't stop there. We go to the next step, step 3, and this is about going from moles of lithium back to grams of lithium. So again, we always know whatever unit is here, it's got to go down there. Boom. And we have this conversion factor. 1 mole of lithium is 6.94 grams of lithium. So we write the 1. Our moles of lithium are going to cancel. And the other side is going to be the 6.94 grams of lithium. And there we go. And this is great because that's what we're looking for, grams of lithium. So now it's time to take out our calculator and calculate this. If you do it all in one shot, like I said, it's perfectly fine. But just remember, what you want to do is make sure you press times before everything you put on the top, and press divide before everything you put on the bottom. So, and the order doesn't matter, just as long as anything on the bottom, you press divide before you put it in. Anything on the top, you press times before you put it in. So we can write it like this, 45.3. Since 32 is on the bottom, we're going to press divide 32. Now the next one, we can ignore the ones. Those won't change the number. The next one has 4 on the top, so we're going to press times 4. And the next one has 6.94 on the bottom, so we're going to press times 6.94. And we get this number here. Now, I want to point something out to you real quick. The answer we got when we did it step by step was 39.4 grams. It's right there, okay? But if you look at the calculator, if I'm rounding it, it would round to 39.3 when we did it all the steps one after another after another. But remember, the last sig fig has a little bit of wiggle room to it. So when we have 39.4, because this is the last sig fig, we're really saying an acceptable answer is somewhere between 39.6, maybe going a little up, or 39.2 going a little down. So 39.3 is effectively the same result. Now, why did this happen? It happens because if you round in each in-between step, sometimes you'll round the number up and then you'll round it up again, and maybe you'll round it up a third time just by random chance. And so the number deviates a little bit from if you did not round in between. But either way, to me and to you as scientists who understand sig figs, both of these answers are equivalent. So that's okay, that if you do it all in one shot like I did, if your answer is slightly different on the last sig fig, that will happen sometimes. Okay, so that's how you can do the same problem, get the same answer, but all in one shot if you like. Did anyone want to ask another question about our first example of stoichiometry here? Okay, so that's the first example. We're going to do another one now, too. But in general, what you saw was there was 3 steps in stoichiometry. And actually, these steps are always the same. They never change, okay? The first step is to go from the grams of substance A to the moles of substance A. In our last example, substance A was oxygen, okay? You use the molar mass to do that, and it will look like this. You don't have to memorize the way this is arranged. Just make sure that your units cancel. That's all you got to do. I don't have anything memorized. For me, I just make sure my units cancel. Then I know I'm right. It's almost foolproof. Next, step 2, that's the only step where you use the balanced chemical equation. So step 2 is where you go from moles of substance A, one substance, to moles of another. And for our last example, substance A was oxygen, substance B was lithium. There you use, that's where you use the coefficients in the balanced equation. It's the only place where you use those coefficients, okay? You never use those coefficients in step 1 or 3, only in step 2. Finally, at the end of step 2, you've got the moles of your second substance, and you often have to convert it back to grams. And for that, again, you use the molar substance of the molar mass of the substance the question asked about. Now, I want to point out something from the last example. Again, notice that our coefficients, like 4 here, is only used in step 2. Never, ever, ever put the 4 here. 1 mole of lithium weighs 6.94 grams, not 4. So the coefficients in the balanced equation only belong in step 2. Make sure you don't put them in the molar masses. The molar masses are always the mass of 1 mole. So that this 4 only goes in step 2. So those are the same 3 steps. And it's always the same 3 steps. So you don't have to memorize these. Just do a few problems. You'll get used to it. And make sure your units cancel. Let's do another example. So how many grams of nickel are needed to make 18.9 grams of nickel 2 chloride? So here our substance A, our first substance that we're given the amount of, is nickel 2 chloride. And our substance B is nickel. So we're going to have to go do our 3 steps, go from grams of nickel 2 chloride to moles of nickel 2 chloride to moles of nickel to grams of nickel. So we're going to have to be going between grams and moles for nickel 2 chloride and between grams and moles for nickel. So we're going to have to calculate the molar masses of each of these. So I'm going to do that up front at the very beginning. So here's the balanced equation, and I say balanced. Is it balanced? Well, maybe we should check and make sure. That's never a bad idea. Well, in this equation, we have 1 nickel here and 1 times 1, 1 nickel. We have 2 times 1, 2 hydrogens here, and 1 times 2, 2 hydrogens. And we have 2 times 1, 2 chlorines, and 1 times 2, 2 chlorines. So we got our balanced equation. We'll use that for step 2, but we're going to need our molar masses too for nickel 2 chloride and for nickel. So 1 mole of nickel, so if we have a nickel 2 chloride, we're trying to find the mass of 1 mole of that. So 1 mole of nickel 2 chloride contains 1 mole of nickel atoms in it. And it contains 2 moles of chlorine atoms. So we'll have 1 mole nickel times its molar mass. And then we also have 2 moles of chlorine, and each mole of chlorine weighs 35.5 grams. Let's double check that on our periodic table here. So looking at our periodic table, we have nickel right here. All right. So nickel, a mole of nickel weighs 58.693 grams. So I've rounded it to 3 sig figs since my original data had only 3. So I rounded it to 58.7 grams. I did keep an extra one here. Either way is fine. So 3 is fine because our data has 3. 4 or more is also okay. Just make sure to at least have 3. For chlorine, molar mass of chlorine is 35.45. I rounded that to 1 after the decimal, 3 sig figs. Since this was a 5, I rounded the 4 up, 35.5. And we've got 2 of those, so we'd multiply that by 2. So we got 1, and again, in nickel 2 chloride, in 1 mole of this, we have 1 mole nickel. And each mole weighs 58.7 grams. So we have 58.7 grams of nickel atoms. We have 2 moles of chlorine. Each one of those weighs 35.5 grams. So 2 times 35.5 is 70.9. All right. Or 35.45. So ultimately, yeah, whoops, I should have kept that 4 or 5. So if I keep the 4 or 5, it works out like this. Sorry. That was a little mistake on my part. But either way, it's close enough. Like I said, the last sig fig is not that big of a deal. But anyway, we add these together. The nickel atoms and the chlorine atoms together weigh 129.6 grams. So 1 mole of nickel 2 chloride is 129.6 grams of nickel 2 chloride. And for nickel, since it's an element, it's easy enough. 1 mole of nickel, we read straight off the periodic table, 58.69 grams. Did anyone want to ask a question about calculating the molar masses for the nickel 2 chloride or for getting the molar mass for nickel? Okay, feel free to ask later if you want. So let's move on and now answer the question we have here. So we have our balanced equation here. Remember, the balanced equation is only going to be used for step 2. And we have our question. We're starting with grams of nickel 2 chloride. We want to get grams of nickel. So we're starting with grams of nickel 2 chloride. Step 1 is always to go for the mole. Okay, go for moles of nickel 2 chloride. So to do that, we're going to use the molar mass of nickel 2 chloride that we calculated on the last slide. 1 mole of nickel 2 chloride is 129.6 grams of nickel 2 chloride. Next, step 2. Step 2 is where we use the balanced equation because we're going to go from moles of our substance A, which was nickel 2 chloride, to moles of nickel, our substance B that we were asked about in the question. And our relationship here on the balanced equation is 1 mole of nickel 2 chloride is made from 1 mole of nickel. So it's 1 and 1. Finally, we're asked in the end about grams of nickel. So we want to go from moles of nickel to grams of nickel. So to go between moles and grams, we use the molar mass. This time the molar mass for nickel. 1 mole of nickel is 58.69 grams of nickel. So let's write our data in this question. The data here is not any of these conversion factors. So we have all kinds of conversion factors here. These are not the data. Oops. These are not the data right here. These are the conversion factors. You can tell because they have equals in them and pers. Our data is this right here in a problem. Number, unit, 18.9 grams nickel 2 chloride. So we're going to write that first, 18.9 grams of nickel 2 chloride. And next, we're going to apply our conversion factor. And even before we turn our brain on, we know what's going down here. What's going down here, folks?
Grams.
Grams, yes, good, good, good. Thanks for answering. Yes, grams of nickel 2 chloride, because we know these have to cancel. We're always canceling every time. We just need to know what number goes with the grams. So if we're looking at our conversion factor, it's 129.6 that goes with the grams. So we're going to put that number right here. And then we can cancel off our grams of nickel 2 chloride. The other side of the conversion factor will be right here. 129.6 grams of nickel 2 chloride is 1 mole of nickel 2 chloride. So that goes right there. We're done with step 1. We have moles of nickel 2 chloride. Ooh, yes. And next is going to be to go to moles of nickel 2 chloride. So we could stop at this point, like we did in the last question. You can always stop and write down your answer. Why don't we calculate it just to be sure that this is right? We could stop and calculate it at any time, or we can keep going. It's really up to you and what you like, your style, you know. So 18.9 divide by 129.6 is 0.1458. So if we're doing this to 3 sig figs, we're going to round the 5 up because this is an 8. So it would be 0.146 moles of nickel 2 chloride. So if you were to stop here, that's what you would write. Okay? But you don't have to stop here. We could keep going if we want to. If we do keep going, we know what has to go down here. It's got to be the same as right here. So why don't we just write that down right now? Boom. Okay. Now, the numbers that we're going to get, because we're on step 2 and we're going from moles of one thing to moles of another, that's the only time where we use the balanced equation. So the number that's going to go with the nickel 2 chloride is 1. So we write the 1 there, put it in orange because it's coming from the equation. We're going to cancel our moles of nickel 2 chloride, and the other side will be the nickel. Now, a lot of people ask me, why put nickel here and why ignore the HCl or the H2? What about those ones? Well, we could always, you know, figure out the moles of those too, but that's not what we're asked to do. We're asked to figure out how much nickel. So that's why we put nickel here. Of course, we could figure out this other stuff too, but we weren't asked about it. Okay, so now we have moles of nickel. And if we were to multiply this, well, it's 1 and 1, so we'd get 0.146 moles of nickel at this point if we were to stop. And then we would carry this forward and apply the next conversion factor. But we don't have to stop. We can keep going if we want. We're going onward to grams now. So again, whatever unit is here, that unit is going there, period. Boom, moles of nickel. And we're going to look at our conversion factor that we already figured out we need to use. It's going to be 1 mole of nickel, moles of nickel cancel. And the other side is how many grams a mole of nickel is. A mole of nickel is 58.69 grams of nickel. Boom. And there we go. And finally, we have grams of nickel. That's what we were asked to get, grams of nickel. We are done. Yes, all we got to do is punch the whole dang thing into the calculator. So let's assume that you didn't stop and calculate these at the beginning or in the middle. So we'll go from the very beginning, 18.9 divide by 129.6. Now we can ignore the ones. We don't have to do any of those. We have 58.69 on the bottom. So we're going to times 58.69. And we get 8.5589, and it goes on and on. We want this to 3 sig figs, so we're going to take the 8, the 5, and the 5. Because this is an 8, we're going to round up, so it's going to be 8.56, and our units are going to be grams of nickel. So 8.56 grams of nickel is the answer. So what we figured out is if we have 18.9 grams of nickel 2 chloride, we can make 8.56 grams of nickel, or we would make that from 8.65 grams of nickel. Any questions on our second example here? Anyone want me to go back and talk about a step again? Okay, you can always ask me later. It's okay. All right, so it's always the same 3 steps. You see it? Same 3 steps, just like before. So we go back to the same, right? Same 3 steps. Whoops, I went back too far. Grams to moles, moles to moles, moles to grams. Same 3 steps. We did that here too, right? Grams to moles, moles to moles of another thing, and then moles back to grams. Always the same 3 steps. Boom. Boom, boom, boom. But depending on the way the question is asked, you may not need all of the steps. They're always the same steps in the same order, but sometimes you don't need every single one of the 3 steps. So the purpose of step 1 is to convert grams of a substance into moles of that same substance. But if you're given moles to begin with, you don't need step 1. So it all depends on if you start with grams or moles. Step 2 is to relate moles of one substance to moles of a different substance. In stoichiometry, you'll basically always need that step. But for the third step is after you get the moles of your different substance, then the third step is to take those moles and turn them into grams. But if the question asks you for the moles of that substance, then you don't need step 3. So make sure to read the question carefully, because you don't always need all 3 steps, but they're always the same 3 steps in the same order. So that makes it not too tough, I'd say, even though it is pretty tough when you're first learning it. So, for example, in this question, which of our 3 steps would we have to use? Well, the question asks how many moles of calcium would react with 18.5 grams of O2 in the equation here. So let's decide which steps we're going to actually need. Well, we're starting here with grams of O2. That's our beginning, grams of O2 right here. So we're beginning with grams. We'll use step 1. That will get us from we'll go for the mole. We'll get from grams of O2 to moles of O2. So grams of substance A, which is O2 in this case, to moles of substance A. Okay. Then the second step is to go from moles of substance A, which is O2 in this case, to moles of substance B, which in this case is calcium. And notice, moles of calcium is what we were asked to get. So once we've gotten to this part, we are actually already done. Step 3 would involve taking the moles of calcium and to turn them into grams. But the question asks for moles. So in this case, we know we should stop at the end of step 2. We stop here. Stop here. Stop here. We don't go to step 3 and get grams of substance B because the question didn't ask for grams of substance B. It asked for moles. Okay. So, yes. We stop right there. Okay. So now, let's actually carry out the problem. So step 1 was going to be to use the molar mass of O2 to go from grams of O2 to moles of O2. So let's do that. Grams of O2 to moles of O2. We calculated earlier that the molar mass of O2 was 1 mole of O2 is 32 grams of O2. So we take the 18.5 grams of O2. That's what we were given in the problem. And again, the unit that's here has to be here. So we just copy it from here down to here. Boom. And then we see that the number that goes with grams in our conversion factor is 32 grams. Then the other side of the conversion factor is 1 mole. So we put that, we cancel our grams, and we put that here, 1 mole. And so now we get out our calculator, and we do 18.5 divide by 32. And we get to 3 sig figs 0.578. And our unit is going to be moles of O2. So now we're at the end of step 1. We did that. Notice again, we put grams on the bottom and moles on the top, so our units of grams will cancel. Really important. Next. We want, now what we're asked for is the moles of calcium. So we need to go from moles of O2 to moles of calcium. When you're going from moles of one thing to moles of another, you use the balanced equation, step 2. Only step 2, you use the balanced equation. So from before, we found out we had 0.578 moles of O2, and we're going to apply a conversion factor. Let the units be your guide. Okay, this moles of O2 is here. It has to go down here. Boom. Right? And we see that from our balanced equation, the number we're going to put next to the moles of O2 is 1. And our moles of O2 will cancel. Then the other side is the 2 moles of calcium. The 2 comes from the balanced equation. And now we're going to have moles of calcium. If we multiply 0.578, we multiply that times 2, we get 1.156. And I want to round this to 3 sig figs because my data started with 3 sig figs. And so I put 1.16 moles of calcium. And that's it. That's what the question asked for, moles of calcium. We stop, we're done. That's the question asked for. So be careful reading the question. Make sure that you know where to stop or where to start. It's always the same 3 steps, but the order might differ. Okay. Any questions there? And want me to go back to a step? Good. Okay. So, in all of the reactions we were looking at earlier, excuse me. In all of the reactions we were looking at earlier, we assumed that we had an unlimited amount of the other ingredients. However, that may not always be the case. Sometimes we don't know which one is going to run out first. We have, let's say, you dig in you're going to make pancakes, okay, like we were doing earlier. So you dig in your cupboard, you figure out, right now I got 3 cups of flour, I got 10 eggs right here, and I've got 4 teaspoons or 8 half teaspoons of baking powder, okay? And you want to know, well, how many pancakes can I make? That's just like the chemistry question, right? How many of this, chemical can I make? This medicine or something, or this plastic, how much of it could I make given the ingredients that I have, the reactants? Well, what we need to do is find out how much product each of the reactants could possibly make if we use them all. Then whichever amount of product that is could actually be made, the least amount, is what would actually be made. And the substance that would run out first when you make that many is called the limiting reactant. So if we look at the flour, 1 cup of flour makes 5 pancakes. So 3 cups of flour could get us 15 pancakes. And 2 eggs makes 5 pancakes. So 10 eggs could make 25 pancakes. And half a teaspoon of baking powder makes 5 pancakes. So 4 teaspoons or 8 half teaspoons could make 40 pancakes. How many pancakes were we actually going to make? Well, we're only going to make 15 because once we make 15, we're out of flour. So flour is called the limiting reactant. And the amount that we could potentially make is called the theoretical yield. So that's a new terminology. Theoretical yield is the amount of a substance that you could make assuming that the reaction goes perfect. So like 15 pancakes is the amount of pancakes we could potentially make assuming that all of the ingredients are used up and the cooking goes perfect and we get exactly the amount we could make from the flour. But in chemical reactions and in recipes, things don't always go according to plan, right? Sometimes part of the stuff that you make is junk and you don't want it, like you burn a few, or it just doesn't make what you want. Often when you're first making your first few pancakes, the griddle isn't hot enough and you get like a half-cooked, not real pancake. This happens in chemical reactions too. There's always side things that are made that you can't really avoid making them. It's just a part of the chemical reaction. And so the theoretical yield is not always achieved. So we should think about what we could actually make given what we're doing with this reaction or recipe. So suppose we cook pancakes and theoretically we could get 15, but actually we burnt 3 and 1 fell on the floor. So in reality, theoretically we get 15 pancakes, but experimentally in reality we only got 11. So we can then use this information to calculate our percentage yield, which is out of the whole theoretical yield that we could make, what part were we actually able to make? Remember, a percentage is always a part over the whole. So in percent yield, our part is going to be our actual yield, the part that we were actually able to make, and the whole is going to be the theoretical yield, what we could have made. So our percent yield is the percentage of the theoretical yield that was actually attained. So again, percent is always the part over the whole and then times 100% to make it a percentage. The part here is the actual yield, the 11 pancakes that we were able to make. The whole thing is the theoretical yield, what we could have made if everything went perfect. And then that's going to be turned into a percent times 100%. If we use our calculator, it's 11 divided by 15, whoops, 15, which is 0.773, and then times 100 to make it a percentage. So 73% to 2 sig figs. Remember, percent behaves like a unit. We can always multiply by 100% because 100% means 1. You can always multiply by 1. Just make sure if you multiply by percent, you're tacking on the unit of percent. So since 4 of the pancakes were ruined, we got only 73% yield. Now, how does this work for a chemical reaction? So for a chemical reaction, this is an example with the chemical reaction. So for the pancakes, we were given how much flour and how much eggs and how much baking powder, and we tried to figure out how many pancakes could possibly be made from these things. And we figured out the flour ran out when we made 15 pancakes. Well, for chemicals, we've got to do the process of stoichiometry to figure out how much product they can make. So the way you'll recognize that you have a limiting reactant problem is that instead of being given one value of the reactants you're starting with, you'll be given 2. So here we're given 2 amounts of reactants and we're not told which one was going to run out first. So what we're going to need to do is do the 3 steps of stoichiometry, but we're going to have to do them for each reactant. One of the reactants is sodium that we start with, the other is chlorine. So we're going to do for sodium, step 1, convert from grams of sodium to moles of sodium. Step 2, convert from moles of sodium to moles of sodium chloride that could be produced in this reaction. And then from there, go from moles of sodium chloride to grams of sodium chloride. Step 1, step 2, step 3. For step 1, we'll use the molar mass of sodium, which is 22.99 grams per mole from the periodic table. For step 2, we'll use the balanced equation. 2 moles of sodium make 2 moles of sodium chloride. And for step 3, we'll use the molar mass of sodium chloride, which if you calculate it, I didn't go through calculating it this time, but 1 mole of sodium chloride is 58.44 grams. And we do step 1, 2, and 3 for chlorine as well. Step 1, go from grams of chlorine to moles of chlorine, use the molar mass of chlorine, which is 70.9 grams. Step 2, go from moles of chlorine to moles of sodium chloride. This is going to use the balanced equation. 1 mole of chlorine makes 2 moles of sodium chloride. Step 3, go from moles of sodium chloride to grams of sodium chloride. And this is going to use the molar mass of sodium chloride, which we saw earlier was 58.44 grams. Okay, so we would do step 1, 2, and 3 for each of these. So here is all the 3 steps. I'm kind of going through this quickly because we did a few stoichiometry problems already. I just want to focus on the concept of the limiting reactant. So again, if you have a limiting reactant here, you'll notice the problem, because in the problem you'll be given two amounts of substances instead of just one like we were in the previous problems. And you'll have to do the 3 steps of stoichiometry. So here we're starting with 53.2 grams of sodium. We're going to put the grams of sodium in the molar mass in the bottom so they cancel. We're going to put them, and then this many grams is, 1 mole of sodium. Then step 2, we use the balanced equation, 2 moles of sodium. Make sure the moles of sodium are at the bottom so they cancel. Makes 2 moles of sodium chloride. Finally, we'll use the step 3 to go from moles of sodium chloride to grams of sodium chloride. We use the molar mass of sodium chloride. So we make sure the mole of sodium chloride is on the bottom so it cancels. And we get 1 mole of sodium chloride is 58.44 grams of sodium chloride. And if we punch this in, we can go ahead and punch it in. So remember, when you punch these in, whatever's on the top, press times before you put it in. Whatever's on the bottom, press divide. It doesn't even matter which order you go in. I'll show you. We start with the beginning number, 53.2. Let's say I type in this number next, right here. Okay. It's on the top, so I'll press times before I put it in. Times 58.44. Let's say I do the 2, this 2 and this 2, divide by 2 since this one's on the bottom, times 2 since this one's on the top. Then this number 22.99 is on the bottom, so I'll press divide before I put it in. We still get 135 grams. Same as if we did it the normal way. Let's do it the normal way just to confirm. 53.2. This number is on the bottom. Press divide. Divide 22.99. The 2's on the top. Times 2. 2's on the bottom. Divide 2. 58.44 is on the top. Times 58.44. And we get 135. And then for the next one, going back to the lab, notice again, we have Cl2. This is not the same as chlorine atom. This is like the same in experiment 3 where we did I2. Okay, a mole of chlorine atoms, just going back to look at chlorine real quick. Oh, I lost my way. Oh my God, my email is going off the hook. I'm going to close that. Okay. This is how many emails I get per day, guys. It's insane. Okay. So remember, 1 mole of chlorine atoms is 35.45 grams, but this is not chlorine atoms, it's chlorine molecules. 1 mole of chlorine molecules contains 2 moles of chlorine atoms. So the molar mass of Cl2 is twice this, and 2 times 35.45 is 70.9. So 1 mole of Cl, yes, that's 35.45. But 1 mole of Cl2, that is 70.9. Okay. Okay, so let's do the calculations now for the bottom row. So it's going to be 65.8. And then we press divide since 70.9 is on the bottom, 70.9. Then the 2 on the next one here, the 2 right here is on the top, so times 2. And then the 58.44 is on the top, so we say times 58.44. We get to 3 sig figs, 108 grams. Okay, so what this means is that if all the sodium were able to react, it could make 135 grams, assuming there wasn't enough chlorine, but there isn't. Because when all of the chlorine reacts, all 65.8 grams, we only get 108 grams of sodium chloride. So we can tell, because the chlorine is able to make less of the product, it is the one that ran out first. When the chlorine runs out, we will have made 108 grams of sodium chloride and no more will be able to be made. There will be some sodium left over, but it won't be able to react because there'll be no chlorine to react with it. So we say that chlorine here is the limiting reactant. And so just to summarize here with limiting reactant problems, the way you recognize that you have one is that you are given 2 amounts of reactant instead of just 1, like in our normal stoichiometry problems. From there, you do the same 3 steps of stoichiometry that we talked about earlier, but you do it for both of the reactants. Then you find out which one could possibly make the least product, and that's the amount of product that will actually be made. That's your true theoretical yield. 135 grams of sodium chloride won't be made. 108 grams of sodium chloride will. So now that is our theoretical yield. Let's say we wanted to determine our percent yield. But before we do that, did anyone want to ask a question? I know I went through this last example since we had done a few stoichiometry examples. I went through this last one a little fast. Did anyone want some clarification on one of these 3 steps of stoichiometry for either sodium or chlorine? Okay. All right. So let's finally, now that we've calculated our theoretical yield, 108 grams of sodium chloride, let's calculate our percent yield. So also given has to be, if we want to calculate the percent yield, the actual yield has to be given. Now, if you're doing an experiment, of course, you'll have your own actual yield based on whatever amount of products you were able to make. But if you're doing a homework question or something, you're not doing the experiment. So you have to be told how much was the actual yield in the experiment. So this question is now saying the actual yield was 86.4 grams. So theoretically, we could have made 108 grams, but actually we made 86.4. So then we say, well, if we want to know the percent yield, it's the actual yield over the theoretical yield. So the actual yield was 86.4 grams. This was given to us in the problem here. The theoretical yield, what we could have made, was 108 grams. And we multiply by 100% to make it a percent. Now again, anytime you hear percent, do I memorize the way this percent works? Not exactly. Every percent is really the same. It's the part that you're interested in. So here we're interested in what we actually got. Over the whole thing that we could have gotten if everything went perfect was the theoretical yield. Then you times it by 100% to make it a percent. So the part over the whole times 100%. And if we calculate this, let's bring up our calculator. We have 86.4 divided by 108 times 100. And that gives us 80 or 80.0. Why did we write, so our calculator told us 80. Why did we write 80.0?
3 sig figs.
3 sig figs, right? If you want to write 80 with 3 sig figs, you can't just write 80. Good call there. So 80, the way it's written here, would indicate 1 sig fig. But both of our other pieces of data here had 3. So our results should be written with 3. If you wrote 80, I'd be like, 1 sig fig? Oh, don't do this to me. Okay, no, don't write numbers with 1 sig fig. It's sad. Okay, yeah, this 80 is an 80 with 3 sig figs. So we write it as 80.0%. Okay, So at this point, we're about at the end of lecture time. We do still have a few more minutes, but I don't think that I can start with energy yet. So in our next lecture, we're going to finish off lesson 17, and we're going to start up on lesson 18. So were there any last questions that anyone wanted to ask as we wrap up this lecture here? Okay, and just an announcement is that if you want to, meet over Zoom and talk about any problems on mastering chemistry or anything like that, tomorrow I'll just be here. I'm going to be creating your gradebook into Canvas and finishing up the last couple labs. So you're going to see some weird things happening with the Canvas grades. That's just me trying to figure out how to build a gradebook in Canvas because I've never done it. But your old scores are already posted for your old homeworks and your old exams from before we went online. So those are in the old PDF fashion, but I'm going to be converting those into the Canvas gradebook, and I'll be doing that tomorrow. And I'll just be in front of my desk, so I might have Zoom open too. If you want me to open it, just send me a quick email if it's not open, and I will do so that we can just chit chat and talk about problems, okay? So if you see things happening on Canvas this weekend with grades, though, don't freak out just yet. I'll be building in the grade book into Canvas. And so that's it. I hope you all have a great weekend. Finish your experiment 3, work on lessons 16 and 17 in Mastering Chemistry. And just so we all feel like a group again, let's all say bye if you like. Bye, everybody. Have a great weekend. Bye.
Thank you.
Bye.
Bye.
Bye. Thank you.
Bye.
Bye.
Good day.
Bye.